Welcome to The Explainer. Today, we're diving into a really beautiful mathematical tool called a direction field. So let me start by asking you a question. How do you find the answer to an equation that you just can't solve? You know, one of those really messy ones that normal algebra just can't crack? Well, the answer is surprisingly simple and kind of beautiful. You draw a picture of it. Seriously. And this is the picture I'm talking about. This is a direction field. Now, it might look a little chaotic at first glance, but it's actually a map that reveals the secret behavior of incredibly complex systems. And I promise, by the end of this, you'll know exactly how to read it.
Okay, so let's get into it. How on earth can we see solutions without actually solving anything? It sounds a bit like magic, right?
So, a little background first. Differential equations are basically the language of change in the universe. They describe everything: how a cup of coffee cools down, how a population grows, you name it. The only problem is, they can be ridiculously difficult to solve with pen and paper. And that is where our amazing tool comes in. This quote really just nails it. A direction field is a graphical method. It's kind of like a cheat code that lets us skip all the tough algebra and jump straight to the good stuff, understanding the shape and the behavior of the solutions.
So what is it technically? Well, a direction field is basically a grid, and at every single point on that grid, we draw a tiny little line segment. The slant of that line, its slope, is dictated by the differential equation itself. It's like a complete roadmap of all the possible slopes for every possible solution.
So we know what this powerful tool is, but how do we actually go about creating one of these maps? You know, the fundamental idea here is shockingly direct. A differential equation like y prime equals some function of x and y is literally just a formula for the slope. You give it a coordinate, any x comma y point, and it spits out the exact slope of the solution curve right at that spot. That's it.
Now you could draw one by hand, and honestly, it's a bit tedious, but doing it just once really makes it all click. You just choose a grid of points. For each point, you plug its coordinates into the equation to calculate the slope. Then, right at that point, you draw a tiny line segment with that exact slope. Do this 100 times or so, and boom, you've made a direction field.
And the person we have to thank for this brilliant graphical method is the legendary mathematician Leonhard Euler. And here's a fun fact so you can sound like a pro. It's pronounced Euler, not Euler. You're welcome. Okay, let's be honest. Picking points one by one sounds like a total drag. It works, but isn't there a smarter, maybe a faster way to build this map?
Yes, there is. It's a clever trick using something called an isocline. So instead of picking a point and then finding its slope, we flip the script. We pick a slope we care about first, like say a slope of 0, and then we find all the points that have that slope. So for the equation y prime equals 0, you can just draw little horizontal dashes all along the x-axis. It's a massive shortcut.
Okay, so once we have our map of slopes, what do we actually do with it? Well, this is where the fun starts. This is where we start threading the solution. This is the big payoff. With our field of slopes all drawn out, we can sketch what an actual solution looks like. All you have to do is pick a starting point, any point you want, and then just follow the flow. You thread a curve through the field, making sure your line is always parallel to the little segments it passes. It's just like a leaf floating down a river, where the direction field shows you all the currents. And there are really only two super simple rules to follow. First, for most equations, different solution curves can never cross each other. They flow in their own lanes. And second, as you draw your curve, its own steepness has to match the little slope markers around it. Basically, just go with the flow. That's it. But these maps can tell us even more. They can reveal some pretty deep truths about a system's long-term behavior, things like equilibrium and stability.
If you ever see a place on the map where all the slope lines are perfectly horizontal, that means the slope is 0. This is an equilibrium solution. It's a state where the system has stopped changing. You know, for our cooling coffee, this is when it finally reaches room temperature. It's the long-term behavior of the system. And what's really cool is that these equilibria have different personalities. A stable equilibrium is like a valley. You can see on the map that all the nearby solutions get sucked into it. But an unstable equilibrium is like a sharp hilltop. Solutions that start even a tiny bit off that line get pushed away, never to return. And you can see all of this just by looking at the direction of the flow on the map. It's amazing.
Now, drawing these by hand is great for learning, but in the real world, let's be real, we use computers. So let's check out some modern tools.
The best part about all this is that you don't have to do it by hand anymore. There are some fantastic, free online plotters that'll generate these fields for you in an instant. Tools like GeoGebra and Desmos let you just type in an equation and immediately see the map. I really encourage you to go play with them. It's the best way to build your intuition.
I mean, GeoGebra, for example, is just incredibly powerful. It's a dynamic tool that brings together all these different parts of math into one engine. You can plot the field, then click on any point and watch it draw the solution curve for you right in real time. It's fantastic. And this is really where it all leads. That simple idea of follow the slope, starting at a point, finding the slope, taking a tiny step, and repeating, that's not just for sketching. It's the core logic behind a super powerful computational technique called Euler's method. It's literally how computers approximate solutions to incredibly complex problems. And that brings us to a final, pretty big thought. Think about the massive computer simulations that predict hurricane paths or global weather patterns. They're all based on huge systems of differential equations. So could it be that at their very core, they're all built on this same simple, elegant, visual idea of just following the slope? Something to think about.